All right, let's talk about going around a bank curve with friction. So we have this question. I'll just read it to you. What will be the minimum and maximum velocities required for a 1,000 kilogram car to travel around a 335 meter radius bank curve at 33 degrees with a coefficient of static friction equal to 0.07? Okay, so first thing we need to do is derive a formula. So I'm going to come back to this in a little bit. Let's come up with a derivation for this. Let's put a car on a curve. Let me draw a little line here. This is the angle theta, which is going to be 33 degrees, but we don't need to know that yet. As we did in class, we took the normal force that's acting on this car, and remember that's perpendicular to the incline, and we broke it into its two components, the horizontal, and I'll do x direction in red. That's going to become important later. So that, let me clean that up. That's going to be the force normal in the x direction. Let me make sure I label this as the force normal, and then in purple we'll go up this way, force normal in the y direction. Now let me zoom in here. Here we go. And this angle here, let's do it in black, be consistent. That angle there, it's not working. There we go. This angle here is theta. And we talked about that in class as to why, but if you don't remember, and I'll put this here in orange just so I could keep it consistent and I can get rid of it. So imagine that this triangle extended down as such. And and if we were looking at this, this was theta. Let's say that was 30. That would make this 60. That would make this 60. That would make this angle 30. And you can see that this angle and this angle are the same. So let me clean that up. So that's not in our face. And let me move this out of the way just a tad so we can see our formulas. Okay, so the force normal in the y direction, this is theta, this is the adjacent side, so this will be equal to force normal cosine of theta, and the x direction will be equal to, this is the opposite side, force normal sine of theta. So I'm going to write these down over here so I know this later. So the force normal in the x direction is going to be equal to force normal sine of theta, and force normal y will be equal to normal force times the cosine of theta. Okay, great. Now, let's take a look at what friction is going to do. So I'm going to slide this over this way. Let me put another car on the bend as such. All right. So here we have our angle theta. Now, if this car, we'll take a look at velocity max first. So as this car is driving around the bend, there's a force of friction that will keep it from flying off the track, and that will be going this direction here, and we'll call this the force static. I'm going to draw a horizontal here. Oops. Fighting with me. This angle theta is equal to this angle theta here, alternate interior angles. Go back to geometry. Let me clean this up a little bit. There we go. And so we can break this into its two components. This will be the force static in the x direction, going to the left, and I believe that should be red. Yeah, make that red. And come up here and do this. That'll be force static in the x direction, and simultaneously it will be pulling down force static in the y direction. Okay, what does that mean? Well, let's take a look. I wanted that to be red. I know it's digital, but I'm going to write over it anyway. Here we go. So let us take these and write down what's happening here. So we have the force static in the x direction will be equal to force static cosine of theta, because this is the adjacent side, and in purple, the force static in the y direction will be equal to, oops, that should be in purple. It's going to make a difference later for my organization. Force status in the y direction, force static y, will be equal to, and remember this is the opposite side, this is force static sine of theta. I'll sign positive and negative later when I'm trying to figure it out. So let's take a look here. That's going to be mu s times the normal force times the sine of theta. And this will be equal to us times the normal force cosine of theta. And so now what I have done is I have taken friction and broken it into its two components and done the same thing with the normal force here. So let me zoom out a little bit so I can look at both of these. Okay, so what? Well, the big beast that I'm leaving out here in the y direction is the weight on this box, mg. Alright, so through the power of digital media, I can highlight all of that, bring this over a little closer so we can see what's happening. Okay. Let's sum our forces in the x and y direction. I will do y first with purple. And let's see what we got here. Sum of the forces in the y direction will equal. Now I am going to assign these directions positives and negatives in the formula itself. So when I put this in, I will use positive 9.8. So that's important to remember. And let's take a look. So G, when we put it in the formula, will be 9.8 positive meters per second squared, a little star here. All right, let's take a look and see what happens here. We have going up right here, force normal, cosine of theta, positive, plus, no, I'm doing the maximum, minus, this is going to be going down, mu s force normal sine of theta, and minus, that's going to be negative, mg. This thing is not flying up into the air, nor is it hurling towards the center of the earth, so that should be equal to 0 newtons. Let's take a look at the sum of the forces in the x direction. Now remember, this is going to give us our centripetal force. So whatever the net force is pulling towards the center of the circular path, that's going to be our centripetal force. So let's take a look and see what we have. We have, going to the left, we'll make that positive towards the center of the circle. We have the force normal sine of theta, and we're going to add to that mu s force normal cosine of theta. And that should be equal to, when we have these two forces together, that should be equal to the mass times the centripetal acceleration, which is v squared over r. Okay, so now let us use our sum of the forces in the y direction and find the normal force. So I'm going to factor out normal force, and that's going to give me cosine of theta minus mu s sine of theta minus mg. I'm going to stop yip-yapping and just do it. I'm going to move mg to the other side. I'm going to take some algebra shortcuts here. And so the normal force on an incline for the maximum velocity will be mg over this quantity here. I'm now going to take this quantity and insert it for normal force here. Alright, so let's see what happens. I'm going to factor out normal force before I do anything, so that I have, this is equal to the normal force times the sine of theta plus us. I always make this mistake and I put the normal force back in here, so let me do this like quietly. Okay, now I'm going to insert this. I'm going to switch to black and make sure I got that. Okay, so what this will be, let me put this group together, mg vinculum cosine of theta minus the coefficient of static friction times the sine of theta, and I'm going to multiply it times this quantity grouped together, the sine of theta plus mu s cosine of theta is equal to the mass times the centripetal acceleration. Don't forget that's equal to v squared over r. Alright, so what can we do here? Well, since this is multiplied, right, a, b, c, we should be able to cancel out the mass. That's important. And we don't want the radius down here at the bottom, so I'm going to multiply both sides times r. And let me rewrite this again. So that would be r times g times this quantity here, sine of theta plus mu s cosine of theta. You might actually see this written gr. I derive the formula every time, so it really switches up for me. So that's, make sure you have that and group together in parentheses. Draw vinculum cosine of theta minus mu s sine of theta. And that will equal v squared. I'm going to switch sides with this, take the square root of both sides, and this will give us velocity maximum. Right, and so it's going to be rg sine of theta plus mu s cosine of theta divided by cosine of theta minus mu s sine of theta is such. Alright, and we can take this value and we can find the maximum velocity. But remember that the radius was 335 meters. Theta was equal to 33 degrees. And mu s was equal to 0.07. All right, let's take a look. Let's fill everything in. This is where you have to do your best with your calculator skills. Break it up into different parts if you need to. I'm going to put units in case somebody else is watching this on YouTube. I took negatives and positives into account when I assigned the directions, so I'm going to use positive 9.8 meters per second squared times, this is one quantity together, the sine of 33, plus 0.0, I'm going to put this in parentheses, 0.07 times the cosine of 33 degrees, double parentheses. Let me extend that over cosine of 33 degrees minus. Remember, when you put this in your calculator, your denominator has to be grouped together. I'm going to double parentheses this so I don't screw this up. Make sure I have that all correct there. Yep, that looks good. And let's put it in the calculator. And through the power of jumping around real fast, I got 49.48. Let me check that against hyperphysics. Oh, my mouse is running low. That's great. Huh? Get that in here. Oh, I guess I gotta allow that. 49.74, close enough. And make sure on my 335, 33.07. I did take some rounding liberties. Yeah, I'm pleased with that. Okay, fair enough. All right, so let us take a look at the unique situation of minimum velocity. Now it's really similar to what we did over here. So let me steal my diagram here that I used for normal force. Let's hope I can just select, just take all this. I'm going to take all of that, I'm going to copy it and bring it over here. And we're going to look at this unique scenario. Okay. So what about the minimum velocity? This is a little bit different, but not much. And I'm going to take my car on the incline, and it's going to come to this point where it's going to want to slide down. All right, so what? So going this way then, keeping it from sliding down is going to be the force of static friction. In the x direction, I'm going to stay continuous with red. That's going to go this way. That's going to be your force static x. Going up and down is going to be your force static y. I can put that in a better spot so you can see it a little clearer. Get this back, force static y. And this angle theta here will equal this angle theta here. We could take this now and give it the same formulas that we did before. The only thing that's really changing is the signs on some of these, and you'll see what I'm talking about in a second. Friction is still pulling up, so that's going to be the force is static. Y will be equal to US. Well, let me do this first. Force static, And this is the opposite side, so this will be sine of theta, and the force of static friction will be equal to mu s times the normal force times the sine of theta. Force static x will be equal to force static, this is the adjacent side, cosine of theta, which would be equal to the coefficient of static friction times the normal force times the cosine of theta. Okay, so we're going to do that same thing we did before. Now, I tried to rush this through class yesterday before the bell rang, and I think I paid the price. So let me zoom out just a tad so we can see everything. And let me sum my forces in the y direction. And that's going to be equal to force normal cosine of theta. This is where we're going to get a little bit of a switch here, because now this is going to be going up, positive. So this is going to be mu s times the normal force sine of theta. Now I'm going to slide over to where we did this before. And when we did it before, you could see right here, we had some negative values. This was pulling down. So, and now it's going to be positive because it's going up. Do not forget, we have mg as well. So minus mg. Again, this is not hurling towards the center of the earth or flying into space, so the net force in the y direction is 0. And I know I'm going to need to solve that for the normal force like I did before, so let me just do that now. I'm going to factor out my normal force. Cosine of theta plus coefficient of static friction times the sine of theta will equal mg. So the normal force for the minimum is going to be mg. So cosine of theta plus mu s sine of theta. And I'm getting sloppy with my vinculums here, so let me draw that here. Get this up. Clean this up a tad. There we go. That makes me happy. And let's find the sum of the forces in the x direction. And remember, we're going to say that the direction towards the center of the circle, your circular path, is going to be positive. This direction will be negative. All right, so we are going to have this value here pushing towards the center. The force normal times the sine of theta. We're going to subtract now because this is going to be pulling to the right in the opposite direction. Mu s times the normal force times the cosine of theta. Nothing else is there. Should equal m v squared over r. Remember, the centripetal acceleration is v squared over r. All right, so let's come down, factor out the normal force. It's going to be sine of theta minus mu s. Don't write the normal force again, like I always do. And v squared over r. Okay, so now we're going to take this value for normal force here and insert it here. Well, I wanted that to be a purple arrow. Didn't work. Let's switch to black. And I'm going to insert mg over the cosine theta plus put that together. And times this quantity, sine theta. And all of that should be equal to mv squared over r. We can cancel that out. And that will leave us with g, oops, how did I end up in red? Oh, it's canceling. G has the sign. You don't have to write the denominator in parentheses. I just like to do that so I remind myself to group them together later. It's going to be equal to v squared over r. And I'm going to take some liberties here. And I ridiculously never found any samples anywhere of anybody finding the minimum velocity. Everybody seems to want to find the maximum velocity. And there's one thing you have to remember. I needed to clean this up a little bit. Sorry. If the coefficient of static friction is greater than the tangent of the incline, it will not slide. So in this case, the coefficient is 0.07 and the tangent of 33 trying to use Desmos here. Tangent of 33 is 0.6494, and that is clearly larger than 0.07, so this object will slide. All right, so let's take some numbers in and see what we come up with. And now you're going to see why I did this the way I did. So I'm going to come over here and I'm going to steal all of this. You can just rewrite it on your paper. I'm going to paste it right here, and we can do some sign changes because it's really exactly the same, except let me get my eraser in here, right here. I want to replace these with red, and you can see what I'm talking about. So this should be negative, and before in the denominator we had a negative value, but now it's going to be positive. So all we had to do is rewrite that and change some signs. Let me get this out of the way. Don't even know what that is. All right, let's put this into our calculators and see what we come up with. All right, then I jumped to the end, and I got 42.45 meters per second for a minimum velocity. And that, kids, is how we do it. All right, so let's make sure we have these two formulas here. Drag this over here. There's the velocity minimum. Subtract in the numerator. Here is our velocity. Maximum. Let's put these next to each other. Sweet. Where did this come from? Alright, pretty much the same formula. The only thing we have sign changes right here. Oh, both of these. Thank you very much. If you have questions, hit me up in class.